Hi, excited to be here. I have a bit of a cold, so forgive me if my voice wavers a bit. So I was excited to be invited, but then I got put in the biomedical section, which will make a little sense in a minute. So usually what I work on is taking images of people's brains while they read, and then correlating those images to computational models of language meaning. And it turns out there's some really interesting relationships there, and as our models get better, we actually become better at predicting what word a person is reading. So that's the usual axis I work on. But actually today I'm going to talk about a different axis that has nothing to do with the brain. So it's a bit of a misnomer that I'm in this section. But today I'm going to talk about how computer models that are trained to see the world actually end up learning something that's a lot like what computer models learn if they learn how to read, for some definition of read. So this is work with my two students, Danush and Chris. Here they're wearing EEG headsets. They regret ever having their picture taken with these on because the whole world has seen it now. Okay, so we'll do a little bit of background business because we're going to talk about convolutional neural nets as well as language models of meaning. You're probably familiar with at least one of those two. And then we'll answer three questions. So first, do convolutional neural nets encode semantics? So is there a relationship between what computers learn when they learn to see and what computers learn when they learn to read? And then we're going to talk about when convolutional neural nets are training, what are they learning and when? And then finally, we'll stop with what can we learn about how adversarial images affect convolutional neural nets by using these semantic models. Okay, so to start with image classification, so quick and dirty intro. So this is a subset of the images in ImageNet. ImageNet is 1 million images annotated with 1,000 categories. It's a remarkable data set and it's completely changed computer vision. It's a very wide range of things in this data set. So I see foxes, I see side view mirrors, there's boats, there's planes, a huge number of things. This is a hard data set to do well on, but computer vision has gotten to the point where it can do very well on this data. A convolutional neural net, sort of a very high level description, takes as input the pixels of an image, and then produces as intermediate representations of the data in these hidden layers. And then it uses those intermediate representations of the data in the hidden layers in order to make a final prediction, that is what is in the image. So I'm skipping a lot of details here. But the main thing that takeaway is that there are hidden representations computed by the convolutional neural net based on the images in the pixels in the image. And those hidden representations are what we're interested in today. So it's been found that the different layers of the neural net, so here the CNN1 represents the very first layer of the neural net, learn things that become more complex as you move up into the network. So the very first layer learns something that looks like edge detectors in different color bands. The next layer starts to learn things that look like curves. The layer after that becomes more complicated, like spirals. And then when you get up into the higher layers, you actually start to get things that look like actual animals. So I see dog faces in the 7th layer. And on the very top, you see some things that look like mushrooms. So things are becoming more complex as we move from the early layers of the neural network to the later layers. And then a quick reminder probably for you for skipgram. Skipgram is also a neural network. It only has one hidden layer, and it takes as input one hot vector saying this is the context word I'm interested in. This is the central word I'm interested in. And what it's trained to do is to predict, the context word, so the words that I'm most likely to see around it. So it wants to produce a probability distribution such that there's high probability for the words I'm likely to see around it. So just like before, we're interested in the hidden representation that this network learns. So what is it about this hidden representation? We've seen a lot of proof that it encodes semantics. So does it have anything to do with our convolutional neural net? So we have two models, one that's trained on images to predict what objects in the image. And we have another model that was trained to predict context words. They're learning about the world in two very different ways. And so what we're going to ask first is, do they learn something that's similar? So do convolutional neural nets encode semantics? So to start with, we have to figure out a way to compare these two spaces. They have different dimensions. And so we could train a model that just predicted one dimension from the others. But we're going to do something that's even simpler and much faster computationally. So what we're going to do is we're going to look at the the words in each one of the spaces and ask how those words are represented in each one of the spaces. So here we can see that in one case we have a 3-dimensional space, and in one case we have a 2-dimensional space. But what we're interested in asking is the distance between words in the space preserved across the spaces? So we can calculate distance no matter how high the dimension is, and we're asking, are those distances correlated? So here we're gonna say is orange. Orange is pretty close to apple in this space. It's also pretty close to apple in the 2D space, same for orange and carrot. So are the distances preserved? So the first thing we're gonna do is essentially calculate the distances between all the words in both spaces. So we get what's a correlation matrix out. So this is just the correlation of the dimensions for each one of the words, and it tells us how similar words are in each one of the spaces. So these, if you're smart, you notice these matrices aren't symmetric. They should be, but the graphics are not quite right here. So what we're gonna do is take 2 concepts out of each one of these spaces. So we'll take concept 1 and concept 2. Let's just say they're orange and tomato for now. We're gonna take them out of the image correlation matrix, the correlation matrix we calculated based on the hidden representations from a CNN. And we'll take them also out of the word vector correlation matrix. So this is, essentially we're doing leave 2 out cross-validation. So we're gonna take out these 2 vectors, and because we're doing leave 2 out cross-validation, we're also gonna remove the 2 columns from those vectors, because they contain information about the test data. So we're gonna leave those out. So now we have 2 vectors that represent the distance for each word to every other word in the data set, the training data set, you can call them. So it looks something like this. You can think of orange has a particular signature in the image data set, and orange has a particular signature in the word vector data set. And so what we're gonna do here is calculate the correlation of those signatures in the image and word vector data set for both orange as well as for tomato. So we're asking, are the signatures of the representations consistent across the 2 spaces? And we're gonna compare that to calculating the correlation, comparing the correlation of the mismatch vectors. So now I'm gonna ask, is the signature for orange similar to the signature for tomato? And vice versa, the signature for tomato to the signature of orange. And so what this does is, if there was no relationship between the semantic representations in these 2 spaces, it would be just as likely for orange to be in image space to be similar to orange in word space as to be similar to tomato in word space. There's no reason that one should be any more similar than the other. So what we're testing is if the relationship between the words is not random, if it's better than random, if the signature of each word in each space is maintained. So this is what we call the 2 versus 2 test. So we have the top equation says, is the signature for orange more similar to the signature for orange and the signature for tomato to tomato than if we compare it to the signature of orange and tomato and orange. So if equation A is greater than equation B, then this what we call the 2 versus 2 test has passed. The representational spaces are more related than random. And the 2 versus 2 accuracy is the number of times we run this test, the % of the time that it passes. So what we're testing is the signature for these different words in the different spaces, does it have a relationship to itself? Is there a consistency in the representation, irregardless of the number of dimensions? So what we're gonna do is we're gonna test with all of the concepts that appear that we found in both the word vectors as well as ImageNet. So ImageNet classes actually have names, and we're gonna match them to those names. And what we're gonna do is do this for all possible pairs. So it's like leave 2 out cross-validation, except we're gonna do it for all possible pairs we could leave out. So it's actually many, many pairs of words. So what we see here is that there is actually a relationship. So on the y-axis, we have what we call the 2 versus 2 accuracy. So you can think of it as how similar the 2 representational spaces are. And on the x-axis, we have early layers of the convolutional neural net to the late layers. And the very first row with the dots is actually just correlating the pixels. So correlating the pixels alone is not above chance. So it's not like the representations match literally what's in the pixels of the image. You need the convolutional neural net to get some of this information. But the very first layer of the convolutional neural net gives us a representation that's statistically similar to skipgram, which to me was surprising. And we ran a few other word vector models here. But aside from the RNN, they were essentially performed identically, and skipgram had the best coverage over ImageNet classes. So we're gonna proceed with just skipgram here. But you can see that as we move through this neural net, this is for VGG16, which is a pretty simple linear neural network. The growth in similarity to skipgram essentially just grows with the depth. We also ran it for some more complex neural networks. So for example, this is called ResNet 50. ResNet 50 has these residual blocks where it has connections that take the input for a particular block and connect it to the output. So what we found was that even the residual connections actually did add a lot to the representation. So that residual connection brought the semantic representation back to being very similar to skipgram, whereas it would sort of dip in between, which is sort of an interesting result. Showed that the thing that ResNet was sort of based on, that residual connection, was actually very useful. We also ran it on Inception v3. Inception v3 is another complicated network also with modules, and we found, again, this is sort of just showing the endpoints of each one of the modules, but within the modules we see a dip in accuracy as well. And this is based on a NACL paper from this year, and the full architecture diagrams are in the supplementary material, and it's really interesting to go through and see how what the behavior is in each one of these modules. So what I've showed you is that models that learn how to see and models that learn how to read, for some definition of see and read, actually learn something that's very similar. And of course, they're working on data that came from the world. They're learning about the world, and they're learning to understand the world in a way that's similar. So I think this is important. I also think it's interesting. And we can use it in a couple ways to further our understanding of what convolutional neural nets are actually doing. Because this is actually pretty opaque. Convolutional neural nets are hard to understand. The new architectures come out, and it's sometimes unclear why the new innovations are any better or worse. And so these are some ways we can use models of semantics in order to understand models of vision. So now we're going to talk about what the hidden layers are doing during training. So you might know that convolutional neural nets are trained with stochastic gradient descent. So what we're going to do is calculate the gradient on each training example or a batch of examples and update our weights. And we're going to keep doing this until the validation accuracy plateaus. And one epoch stands for going through your data one time. So your whole data set one time. The experiments I'm going to show you here are trained on FractalNet, or for training of FractalNet, which is a different CNN, and for CFAR 100, which is kind of like ImageNet but smaller. Still an object recognition task though. So these are the typical graphs you would see when you're training a neural network. We see that the error goes down on the train and test error, but the test error actually starts to plateau at a particular point, and then we stop training once our test error stops going down. So the questions we're interested in asking here are, where will the 2 versus 2 accuracy rise first? So which layers are learning first? Remember, we have a convolutional neural net. It has these different layers along a depth of a network. And the question is, which layers are doing the learning first, and then which layers sort of learn last? Or do they all learn at the same time at the same rate? Is, I guess, another possibility. So I can have a drink while you think about that. So maybe you formed a hypothesis, and now we'll see if your hypothesis bears out. So here, again, 2 versus 2 accuracy on the y-axis. X-axis here is now epochs, so as we go through the training of the network. And the different colors correspond to different layers of the network. The most purple ones are early, and then as they become more yellow, they become later in the network. So what we can see here is that those early layers, they learn fast. They learn right away, and then they stop. And then the later layers, they learn more gradually at first, and then they sort of plateau at the end. But most of the reduction in error towards the end of training is driven by those mid to late layers. And so we're seeing here that in retrospect, it kind of makes sense. If the late layers are based on information learned by the early layers, those early layers need to learn first, right? But this way of using semantic models in order to probe a convolutional neural net allows us to see that very clearly. The last thing we're going to talk about is hidden representations for adversarial images. So adversarial images are really interesting. I think they've generated a lot of interest in the computational computer vision field. They're this idea that you can make very small changes to an image. They would be almost imperceptible to you and me. They certainly wouldn't change what you thought was in the image, but they can completely fool a convolutional neural net. So here's some examples. So I can take a bus, a school bus, and apply the middle picture here is the noise that we would add. And it becomes essentially, to you and me, it still looks like a school bus, but the convolutional neural net thinks it's an ostrich. So we can do this for a bunch of different image types. In each case, the change in the image is, it's not quite, I wouldn't say imperceptible. You can tell the image is more noisy. But you certainly aren't fooled into thinking any of these are ostriches. But on the other hand, the convolutional neural net is very sure that these are ostriches. So the question is, can we use the semantic models that you and I are so familiar with in order to understand what's happening during these adversarial attacks? So to do this, we need to do something different. I need to introduce you to the 1 versus 2 test. So now we have only one image, and it's the adversarial image, and we're gonna ask if this adversarial image has a signature that looks more like the true class, which is what you and I would think, it's the school bus, versus the predicted class, which would be the ostrich. So does the signature for the adversarial image match the true versus the predicted class? So we have, we're gonna take 100 images that are not adversarial and for which we know the true class. And we're gonna compare our adversarial image to each one of those. So we're gonna get the signature for our adversarial image in a space that contains things that we know the class of and that are not adversarial. And we're gonna compare that to the true and predicted word vectors. So for the same 100 image classes, we're gonna get those word vectors, and then we're gonna correlate the true and the predicted word vector to those two sets of, that one set of 100 word vectors. And so if the adversarial image has a signature that's more like the true class, this green arrow will be shorter. If it has an image that's more similar to the adversarial or predicted class, then the yellow line will be, the red line will be shorter. So essentially we're asking, has the signature shifted? Does the signature actually start to look more like the adversarial class? And this allows us to test some things. First I'll tell you about the actual method we use to make the adversarial images. It's called the momentum iterative method. And essentially, you get to choose the adversarial class, which is interesting. So we can decide how hard to make the adversary. So either it's a very similar thing or it's a very different thing. But it requires access to the network, so it's a white box method. So it requires that we're able to see the weights that are inside the network. And so we make very small changes to the pixels, and that moves the network towards making the prediction we want to make. So here's some examples, and they're a lot like the previous ones. We see some noise in the middle. It's Alps on one side, then it's dog, pufferfish, and crab, so sort of similar to what we saw before. So now we're gonna choose 6 target classes based on the similarity of the word vectors. So that is, we're gonna sort all of the possible word vectors we have by the similarity of the true class. And then we're gonna choose some really hard ones. We're gonna choose the one that's most similar to the true class as a target. So that would be very hard to differentiate. It's probably something like cat versus cougar or cat versus dog, things that look similar. One that's least similar, so the very far away in semantic space, and then a set of 4 in between. And now the question is, for over the average of those 6 different difficulties, where do you think the model is fooling the network? So do you think sort of the adversarial attack is working on those very first layers? Do you think it's working on the later layers? Do you think all the layers are affected? Again, I'm gonna have a quick drink while you think about it. Okay, so it turns out that the early layers are actually not very affected. So here on the y-axis, we have 1 versus 2 accuracy, and the x-axis is early to late layers. And those early layers are actually, they know what the true class is. The representation is closer to the true class than the predicted class. They're not fooled by the adversary. It's not until we get into the later layers that this fooling starts to show up, that we start to see it drop below 50%, which means that we're closer to the adversarial class than the true class. So the early layers are not being affected as much by the adversarial attack. It's those later layers that show the effect. So this is for all of the different sort of classes of hardness, the most similar to least similar of the adversarial class that we chose. And what's interesting here is that the most similar actually doesn't show much in the way of difference. So because the 2 classes are so similar, it's actually really hard for our technique to tell them apart. But for the very different classes, the very different word vectors, we're able to see this similar pattern where the early layers are not fooled. So there's some interesting things that could come out of this. We could build better adversarial attacks possibly, or we could also build better models that are more robust to adversarial attacks. So quickly, just to summarize, we talked about, I showed you that convolutional neural nets learn something that looks a lot like semantics, even though they're trained on images. And then during training, the early layers of the convolutional neural net are the things that learn first, followed by late layers. And then finally, adversarial attacks actually attack the later layers. And this is probably because of an accumulation of errors. So very small changes in the input, they don't affect those first layers very much, but then they sort of snowballs and makes the final prediction to the adversarial class. With that, I'd like to thank you, as well as my sponsors. Do we have time for questions? I don't know. If there's questions, I'll take some questions.
Because a problem in language is you're trying to fit every level of abstraction of meaning of words into one damn vector, and there's a big question of what words operate at what level of abstraction. And interesting thing about CNNs is that the different layers can represent different levels of abstraction. So did you ever explore seeing if comparisons the other way or probing the other way, where you use the layers of the CNN to see what kind of words would be fuzzy, maybe a lower level of abstraction, as opposed to cat, which is maybe a higher level of abstraction in the layers?
It's interesting. I haven't thought about that, but it's interesting to think about whether you could solve inference problems by using different layers of the neural network, which might have different sort of generalizations of meaning. That's interesting. We haven't done that. Using the main microphone. Excellent
yeah, is this working? Yeah. Okay, so, I was thinking about how to combine what you're saying with Tishby and information bottleneck. I would have thought that from his perspective, the things that are anchored either close to the inputs or close to the outputs would be pretty stable, and the things that are farther from the observations would be more at risk. And I wonder if what he would say, I don't want to put words in his mouth, is that maybe what you're identifying is an opportunity for improvement, and that our methods ought to be doing best when they're grounded close to observations, and the weakness should be when you're farther from that. And if you're observing something else, that means there's an opportunity to do something better than what we're doing.
Right, so I completely agree with you on that. I think there's a lot of follow-up work here. Some that's pretty obvious, that I think if we used word vectors during training of convolutional neural nets, like you're saying, to bring sort of it closer to the input or output, giving it another signal, I think could make it train faster or better models that are possibly more robust to adversarial images. But I think you're right that there's an opportunity here for a language to help vision, and possibly for vision to help language, that there's a relationship between what these models learn, and if we help them to learn at the same time, we can do better. Good. Okay, great. Thanks so much.